In this video, we will talk about the temperature dependence of kinetics, particularly how we can determine what the rate constant will be at various temperatures. Previously, we have stated that the rate constant is temperature dependent. So changing the temperature changes the rate constant, which is in the rate law. Back in the late 1800s, Savante Arrhenius investigated the relationship and showed the following expression. The rate constant, which is a function of t, is equal to A, which we will call the frequency factor, times e raised to, and this e is our mathematical e raised to the negative of EA over RT. In our previous video, we had talked about how this particular part here comes from our collisional theory. We call this entire expression the Arrhenius equation. And the other important part is that this T value, the temperature, needs to be in Kelvin. R is the gas constant. We will be using 8.314 joules per mole Kelvin. A, this term here, is called the frequency factor, sometimes called the pre-exponential factor, or the A term in the Arrhenius equation. This pre-exponential factor is similar to the value that we find from collisional theory, but it includes additional consideration from the transition state. So it's not just the orientation required to have a successful collision and the frequency of collision, it also includes the terms from our transition state theory, which talk about the amount of rearrangement needed to form that transition state. So this A term includes all the collisional theory components as well as an accounting for the transition state theory. So this pre-exponential factor, or the frequency factor, which would be a value that you would either be given or have to calculate, is approximately equal to the frequency of successful collisions times the frequency of collisions times an exponential term that includes the change in the entropy, which we will be talking about in several chapters, what entropy means, of the transition state divided by our gas constant. EA is the activation energy. Essentially, the activation energy, again, is the barrier that is required for the reactants to transform into the products. It's a measure of the bonds that are broken and the bonds that are formed as we transition from the reactants to the products. It is the minimum amount of energy needed for the reaction to occur. Now we can take our Arrhenius equation and do some mathematical manipulations. Particularly if we're interested in accessing this activation energy, it's up in the exponent. And as we had seen previously, a way of getting access to the exponent is by taking the natural log of our equations. So if we take the natural log of both sides, we will get the natural log of KT, or the natural log of our rate constant, which is a function of temperature, being equal to the natural log of A minus EA over RT, or we could also call it minus EA over R times 1 over T. Now this expression here is a linearized form. It follows the y equals mx plus b format, where b is our y-intercept, which is the natural log of our pre-exponential factor, or our frequency factor. M is the negative of the activation energy divided by our gas constant. For a graph where we are putting the natural log of our rate constant as a function of temperature on the y-axis, and on the x-axis we're plotting 1 over temperature. This temperature here needs to be in Kelvin in order for our units to cancel out. Now, if we're interested in looking at the difference between two temperatures, one of the things we could do is look at a change in y value. The way you would do that is by subtracting two sets of the linearized equations, one from the other, essentially taking y2 minus y1, where y2 is done at T2 and Y1 is done at T1. If we take Y2 minus Y1, and each one of those Y values is equal to the natural log of the rate constant, which itself is a function of temperature, we get for Y2, this would be the natural log of quantity K, which is a function, plugging in the T2 value, minus the natural log of K, plugging in the T1 value. Because each one of our Y values is equal to our mx plus b, or we could think about it as the natural log of kt is equal to natural log A minus EA over RT, we can replace each one of these natural log values with ln A minus EA over R with a corresponding t. This value here corresponds with our natural log of K of T2, and we're going to subtract this value here, which corresponds with our natural log of K of T1. Now, one of the rules for natural logs is if you are subtracting one natural log from the other, you can take that as the natural log of the ratio of the two. So we re-express the left-hand side as the natural log of K of T2 divided by K of T1. Over here we can see that our natural log A values are going to cancel each other out, right? Because we are taking one minus the other. And then we have this common term minus EA over R in both of our values. And so we can pull that outside, giving us minus EA over R times the quantity 1 over T2 minus 1 over T1. This expression here will enable us to, given a rate constant at one temperature and the activation energy, determine the rate constant at a different temperature. Or, if we are given the rate constants at two temperatures, K at T1 and K at T2, we'll actually be able to figure out the barrier for our reaction, which is our activation energy. We will now do just that sort of process. So what we will do is look at a problem in which we are given the activation energy. Here is our activation energy, and we're going to try to determine the rate constant at an elevated temperature. So let's say we have a reaction that is found to have an activation energy of 38.0 kilojoules per mole. If the rate constant for this reaction is 1.60 times 10 to the second power per mole per second at 249 Kelvin, what is the rate constant at an elevated temperature of 436 Kelvin? So there's two different ways that we can go about solving this problem, and we will go through each. Our first method is to find our pre-exponential or our frequency factor. So we will first find A and use A to plug that into the Arrhenius equation to find our K value. So our Arrhenius equation is K, which is a function of T, is equal to our frequency factor times e to the minus EA over RT. We can do some mathematical manipulations to solve for our A value. If we divide both sides by e to the minus EA over RT, e to the minus EA over RT. On the right-hand side, that e raised to the EA over RT cancels out. So we have an expression for A, which is A is equal to our rate constant at a particular temperature divided by e to the minus EA over RT. Now, one of the things we need to be careful about is our units. The activation energy that we're given, the 38, is in kilojoules, whereas the R value that we will commonly use will be in joules per mole Kelvin. So what we're going to do is I'm going to take our kilojoules, shift the decimal place 3 to the right, and that will convert it into joules. So plugging in our K value, this is 1.60 times 10 to the second, molar -1, seconds -1, divided by E to the negative EA 38000 joules per mole. Right, that is converting our kilojoules to the joules, divided by our 8.314 joules per mole Kelvin times our temperature in Kelvin, 249 Kelvin. Right? All that's within the set of parentheses is in the exponent. Now, in terms of our units, the joules cancel out, the moles cancel out, and the Kelvin cancels out, which is good because anytime you have values that are going into an exponent, the values in the exponent need to be unitless. So if we put this all into the calculator, we will get 1.49954 times 10 to the 10th molar -1, seconds -1. That's a -1. Okay, we can now try to find our K value at the elevated temperature. So K at 436 Kelvin. We're going to use our Arrhenius equation. So this is equal to A e to the minus EA over RT. A e to the minus EA over RT. Plugging in our values, that's 1.49954 times 10, 4 times 10 to the 10th, molar -1, seconds -1, times E to the minus EA over RT. Again, we need to make sure that our units cancel out. So to the negative quantity 38000 joules per mole divided by 8.314 joules per mole Kelvin times, now this time our temperature is 436. In parentheses. So if we plug this into the calculator, we get a K for our 436 Kelvin as being 4.20 times 10 to the 5th molar -1, seconds -1. Okay, for our second method, we will need a bit more space, so I'm going to erase a good portion of this and rewrite the answer up top. Now, the second method is going to involve using our equation that we had from before when we subtracted the two linearized equations of the Arrhenius equation. So just as a reminder, that was the natural log of K of T2 over K of T1 is equal to minus EA over R 1 over T2 minus 1 over T1. Okay, so in this case, we are trying to find our value that is over here. So we'll need to try to get that all by itself. The way that we're going to do that is we need to undo the natural log here. So the way that you undo a natural log is take E raised to the value. So we're going to raise both sides. Well, we'll take E raised to both sides. So that would be E raised to the natural log of K at T2 over K at T1, which is equal to E raised to the negative EA over R 1 over T2 minus 1 over T1. Okay, now the e raised to the natural log, these two cancel each other out. So we'd be left with k at T2 over k at T1 is equal to e raised to the minus ea over r times the quantity 1 over T2 minus 1 over T1. We're interested in that top value, k of T2, so we're going to multiply both sides by k of T1 to move it to the right-hand side. That will give k of T2 is equal to k of T1 e to the minus ea over r 1 over T2 minus 1 over T1. Right? Essentially, I took my k value here, multiplied both sides by it, which shifted it over here to the right-hand side. Now I can plug in my values. So k at 436 Kelvin is equal to k at T1, 1.60 times 10 to the 2 molar -1 seconds -1 times e raised to the minus ea, so that's 38000 joules per mole over r, which is 8.314 joules per mole Kelvin. My joules cancel out, my moles cancel out. Multiply that by 1 over T2, which is 436 Kelvin, minus 1 over T1, 249 Kelvin. That is a 4. Okay, and now our units, we have 1 over Kelvin times 1 over Kelvin. So our Kelvin will cancel each other out, leaving us something on the top of our exponent that is unitless. Plugging this all into your calculator, this should equal what we had before, right? Because there's two equivalent methods for solving this. This is capital K, as in that's our temperature in Kelvin. We get 419,985 molar -1 seconds -1, which is equal to 4.20 times 10 to the 1, 2, 3, 4, 5 times 10 to the 5th molar -1 seconds -1. So you can see that either way we do it, we end up with the same answer, either doing it method 1 or method 2. Either one is perfectly valid. One involves first finding the A value, then plugging that into the Arrhenius equation to find our rate at the new temperature. The other one involves using our two linearized equations, taking one minus the other, using this equation here, and then solving for our K at T2. Either one is perfectly valid. The first one you would use primarily if you're interested in also having that the frequency factor.